Hello, everybody. Welcome to session 3 of I3D for modeling and content. Today, we have 4 papers that will be presented by the authors. One of the papers is actually from the TVCG journal, and it will be presented today. Let's start by introducing the co-authors and the authors and the presenters of these 4 papers. So the first paper is titled Contour-Based 3D Modeling Through Joint Embedding of Shapes and Contours, and is authored by Aobo Jin, Qiang Fu, Jigan Deng from University of Houston. And the speaker of this first paper is Aobo Jin, which is a PhD student at the University of Houston. And he holds a Bachelor of Science degree from Electrical Engineering from Dalian and a Master from the University of Houston, where he's advised by Professor Jigan Deng. His research interests include computer graphics, sketch-based modeling, and computer animation. So this is for the first paper. The second paper will be user-guided 3D reconstruction using multi-view stereo with co-authors from Chalmers University. The co-authors are Sverker Rasmussen, Erik Sintorn, Ulf Arsson, and the speaker will be Sverker. So Sverker is a PhD student at Chalmers University of Technology in Gothenburg, Sweden. He's advised by Professor Ulf Arsson, and his research interests led the intersection of vision and graphics. In particular, he tries to make 3D content creation more accessible to the masses. And the next paper is the TVC journal entry. So this actually is a collaboration in between the New Jersey Institute of Technology, UCLA, and UMass at Boston. And is co-authored by Tomer Weiss, Alan Littenecker, Noah Duncan, Masaki Nakada, Chenfang Fujiang, Lapfai Yu, Dimitri Trisopoulos. And the speaker will be Thomas Weiss, which you can wave if you want. And Tomer Weiss is an assistant professor at the New Jersey Institute of Technology. He holds a PhD from UCLA and was a research scientist at Wayfair in Boston. And his research interests include computational design, mixed reality, real-time methods for visual computing. Amongst his feats, there's actually a Best Paper Award at the ACM SIGGRAPH conference on motion in games in 2017. And finally, the last talk will be on progressive regularization of satellite-based 3D buildings for interactive rendering. And the authors are Xiaowei Zhang, Chris May, Jen Nishida, and Daniel Aliaga from Purdue University. The speaker will be, there will be 2 speakers for this presentation. We have Xiaowei Zhang and Chris May. So Xiaowei is a PhD candidate from Purdue, is under the supervision of Professor Daniel Aliaga, and his research interests include procedural modeling and inverse procedural modeling for 3D Euro models using deep learning techniques. And the second speaker, again, is a PhD student from Purdue University, Chris May, and he has a bachelor from Purdue in 2013, and his interests include graphics, image processing, 3D reconstruction, urban modeling, and deep learning. So these are the 4 papers that will be presented today. My name is Andrea Tagliasacchi, and I'm a senior research scientist at Google Brain, and I'm a adjunct faculty at the University of Toronto. And now the stream will go live, and we'll be back at the end of the stream of the video for Q&A. So list your questions on Discord or on YouTube, and we'll be asking the questions for you to the authors. See you soon.
I'm Aobo Jin from University of Houston. My topic is contour-based 3D modeling through joint embedding of shapes and contours. Here is the overview. I will talk a little bit of background and introduce some related work. Then I will show our method in details. After that, I will conclude our method. Currently, several modeling softwares are widely used to improve the experience of modeling process. Different softwares focus on different aspects, like Autodesk Maya more focus on animation and render. Autodesk Matchbox focus on mimic the sculpture process to model an object. Houdini focus on simplify the generation of particle effects. However, those softwares are hard for beginners to use to create preferred 3D models. Experienced modeling artists still need a quite long period to generate a fine 3D model. Sketch-based modeling system is proposed to simplify this 3D modeling process. There are 3 steps. First one is sketch acquisition. Tablet is most popular input device to collect sketch directly. At the development of VR, the VR controller is another functional device to collect sketch. The second is sketch filtering, which is basically extract sketch features. Those features are then used to generate 3D model. Deep learning framework is widely used in feature extraction area and provides to have a great effect. The final step is sketch interpretation, which is generate 3D model based on the extract 2D sketch features. The existing sketch-based modeling system requires semantic lines or alignment process. Semantic lines required to provide the depth information for the modeling system to generate good pillow model as shown in Li et al. The alignment problem exists in all multi-view sketch-based modeling systems since they view dependent on each other, like Lun et al. To simplify the modeling process, several work use divide and conquer algorithm to split the complexity object to several simple objects. However, it's time-consuming and tough work for a beginner to define one object with different parts, like the modeling process of head of bear in Naty et al., the dragon in Jingold et al., and the airplane in River et al. Hoffman et al. Proposed a sniping technique by sniping simple 3D geometric primitives to 2D sketch, then improve the model globally by inferring geosemantic constraints that link the different parts. This work can only focus on simple object structure. Second scheme by Poly et al. Is a state-of-the-art sketch-based modeling system for armor models. Pan et al. Work requires 3D sketch input instead of 2D sketch. Delano et al. Can only generate man-made object. Li et al. Proposed the state-of-the-art sketch-based modeling system generate the surface, which is usually flat, even though the sketch input given the structure information. Our work first want to simplify the input sketch. Only occluding contours are used. Second, we desire to simplify the modeling process. Our method can directly generate a whole 3D model with the sketch input. By doing this, we first collect the 3D models and the relative sketch. The occluding contours are used to train VAE network to build the embedding space. Each point on the embedding space represents one 2D sketch and can be decoded to a sketch through the VAE decoder. The volumetric 3D model are used to train the volumetric autoencoder to project the 3D models onto the embedding space. In this way, 3 points on the embedding space, which represent front, top, and side view of one 3D model, can be used to generate the 3D model through the volumetric decoder. As shown in the example, combine the sketches vectors on the embedding space. The preferred 3D model can be generated through the volumetric decoder. We extended the data by uniformly generating 50 random viewpoints on a bounding sphere whose center is the same as the geometric center of the enclosed 3D shape. After that, we employ an existing non-photorealistic rendering algorithm to generate occluding contours from the front, top, and side views for each 3D projection case, and record the 3 views relation at the label as shown on the right. The VAE architecture we proposed in this work shows here. We use 4 convolutional layers in encoder and 4 deconvolutional layers in decoder. The loss function is construction loss between the generated sketch and the input, and combined with KR loss. This is the volumetric ordinate encoder architecture we proposed in this work. We use 3D convolutional layers in encoder and 3 deconvolutional layers in decoder. The loss consists with the reconstruction loss and view loss. The reconstruction loss is the difference between the generated volumetric representation of a 3D model and the input. The view loss measures the difference of the 3 view latent vectors y generated by the volumetric encoder with the VE encoder output y hat, given 3 views occluding contours of one 3D model. The VE architecture creates embedding space with the 2D sketches. Each point on the embedding space represents one 2D sketch. The smaller distance means most similar shape of 2 sketches. The dog and horse sketches have small distance since they are similar shapes. Meanwhile, 3 views of one object, front, side, and top view, can be combined and decoded to represent the 3D model like the chair and horse. We propose 2 applications with the joint embedding space. First one is SketchBased Modeling. With the sketch input, the smallest distance point with the input can be selected by iterate the samples on the embedding space. Since the other 2 views are bind with the one we selected, so we're utilizing these 2 views and combined with the input view. Through the decoder, the desired model can be generated. Another application is manipulation. The input is the model that we want to be manipulated and the sketch that used to do the manipulation. Through the volumetric encoder, 3 vector representation of 3 views can be obtained, and by exchanging the front view vector with the input sketch vector on the embedding space, 3 new vector representation of 3 views are get, and the desired model can be get through the volumetric decoder. To illustrate the embedding space can embed 3D model with 2D sketches. Here we show the contours generated by the non-photorealistic rendering method given a 3D model, and by the VE decoder given 3 latent vectors generated from the volumetric encoder. The generated sketches are similar with the non-photorealistic rendering result. Here we show some modeling results here. We first generated voxel representation and used Marching Cube's algorithm to smooth the result. The proposed method not only can model man-made objects like glass and table, but also can model the free-form object like fish. Xie et al. Proposed a retrieval-based method to retrieve different parts of one object from a given dataset and do part assembly to generate the final result. Since this method requires a large dataset, so if one cannot find similar parts like the back of the chair at top and the foot of the chair at bottom, the result will be bad. On the other hand, our method can have generation ability, so the generated model can good fit with the input sketch. By comparing with Li et al., our method requires simple input sketch and no thematic curves are required. Our method can generate a decent model compared with Li et al. We also compare the LU value between generated model with the ground truth representation as voxel by using the front view of the model as input for different categories. Our method gets the highest score in all those categories. Our method has some limitations. First, our method only focuses on the generation of cross 3D shapes. Since our method only can generate 3D models with cross surface details, certain small-scale surface details cannot be generated. Besides, due to the potential noise in the generated voxel representation, the results might need filtering, smoothing, or refinements based on the symmetry of the shape or other geometric constraints. Second, our method can only generate 3D models whose occluding contours are similar to those of the shapes in the dataset. If the input sketch is significantly different from any shapes in the dataset, our method may fail to produce desired results as top example. Third, if the 3 orthogonal views of the input contain overlapping geometry, our method could fail to handle such cases, as bottom example. To conclude, we propose a novel sketch-based modeling system by creating a joint binding space. The joint binding space can also be used to manipulate a 3D model. Thank you.
Hi, I am Sverker Rasmusson from Chalmers University of Technology. Today I will present our paper, User-Guided 3D Reconstruction using Multiview Stereo. As you can see in the video, we have developed an interactive tool that enables a user to construct 3D models using quads, while aligning the geometry to a set of photographs using a Multiview Stereo algorithm. The main idea of our paper is to try to separate the problem of reconstruction into 2 parts. One part which is easy for the user but hard for a computer, such as visibility and topology. And one part that vice versa is easy for a computer but hard for a user, such as aligning geometry correctly in world space with respect to a set of photographs. Okay, I will start with going over some background. There is a high demand for creating photorealistic assets for use in games, movies, and industrial and architectural applications. To create highly realistic and detailed environments, a high number of such assets are often needed. It is therefore important to be able to produce these efficiently. So how does one produce such assets? There are a number of methods in use, which I for simplicity will put in 3 different categories. One category is to create the asset manually using standard modeling practices. This is probably the most common route in use today. While this method works, it is of course very labor-intensive and thus costly, and is very much dependent of the skill of the individual artist. There is also no guarantees of the objective accuracy of the modeled object to the real-world one. Fully automatic reconstruction methods have gained traction in recent years. Typically some kind of capture dome is used, where a high number of professional-grade cameras are surrounding the object in a fixed arrangement. Another alternative are systems where the input is a collection of photographs, typically taken with the same camera. While these methods are maturing fast and today can reconstruct many types of challenging scenes, they still struggle with some important parts of the reconstruction. Since they don't have any prior information of the underlying geometry being scanned, they typically use a very high uniform sample rate. This can lead to problems of oversampling, such as introducing undesired noise. This also leads to the model having arbitrary topology. For these automatically scanned models to be useful in practice, significant cleanup and retopologization is often needed as a post-processing step. Our method falls into the 3rd category, semi-automatic and interactive methods. These methods use some form of manual intervention as a baseline, while utilizing automatic algorithms to help the user achieve the desired result. Examples are Sina et al., who uses interactive modeling with the structure from motion for architectural modeling. Su et al. Uses a similar method, but instead applies it to mechanism modeling using a sketch-based approach. Our method shares some characteristics with Habeck and Cobalt, who also uses a variational approach to optimize a 3D mesh. However, our approach is unique in that it uses a much more conventional modeling approach, and a key aspect is that it should work as a drop-in replacement for standard modeling, for the special case of modeling real-world objects. I will now go through some pros and cons with our method. Our method is interactive, which enables the user to provide information that is very hard for a fully automatic method to infer. The user can construct a desired topology. The user can see which part of the geometry that is visible from each camera. And the user can see where a flat primitive can reasonably approximate a surface. Finally, the user can easily distinguish foreground from background. As mentioned, our method also aligns with standard modeling practices. The cons is that manual modeling is still required. However, the user only have to outline a very coarse version of the mesh. Subdivision and the automatic alignment algorithms handles much of the rest. The skill level required to accurately model a real-world object is thus significantly lower than for the fully manual case. So how does this list compare to a fully automatic method such as a photogrammetry pipeline? A fully automatic method does not need the manual interaction required by our method. However, as we can see in this video, in practice, significant cleanup and retopologization is needed as a post-processing step. The total amount of manual work needed for a usable reconstruction is thus roughly the same. With our method, however, we get the added benefit of user interaction while reconstruction, instead of just as a post-processing step. This makes the information provided by the user accessible to the reconstruction algorithm, and provides a much more ideal condition for it to work under, which increases its probability of success. I will end the introduction by talking a bit about topology. Why is it important? Here we see an example of how the topology can differ with our method compared to a fully automatic photogrammetry pipeline. The topology in the lower model is a jumble of tiny triangles with arbitrary topology. This is undesirable for many reasons. One reason is for performance, since the polygon count in the lower model is very high. Texturing and UV unwrapping is also much harder to do because of the big difference in triangle size and shape, and that it doesn't follow natural seams in the object. It is also very important to have a reasonable topology when rigging a model for animation. I will now briefly describe how our prototype application works. The input to the application is a set of calibrated photographs, i.e. a set of images for which intrinsic and extrinsic camera parameters for the corresponding cameras are known. We have implemented a simple prototype that supports the basic features of a modeling application: point and click, quad modeling, moving and dragging vertices and quads, undo, redo, and visualization. The modeling is performed on top of the captured photographs. To start the reconstruction, the user chooses a subset of photographs, typically 2 or 3, in which a particular area of the model is visible. One of these photographs are chosen as the reference photograph. Modeling will take place on this photo, and later optimization will not alter the topology specified in this image. In other words, vertices are only allowed to move in the corresponding view ray direction for this camera. For the other photos in this subset, this direction corresponds to moving vertices along the epipolar line. The workflow is typically structured by first creating a coarse topology of the model. The user can then apply subdivision to get higher tessellation. This mesh can then be automatically optimized to align with the photographs. Each quad will remember which subset of photos it was constructed from, to ensure correct visibility. That concludes the description of the modeling system. I will now go into more detail regarding the multi-view reconstruction. To be able to automatically align the constructed model to the input photographs, we use a multiview stereo algorithm. In short, this means that the algorithm tries to align the geometry in a way that minimizes a score function with respect to the photographs of the model, while keeping desired properties of the geometry, such as smoothness. For photo consistency, we use a modified sum of absolute differences score that generalizes to more than 2 images. For details, see the paper. After each quad placement, we try to align it according to our score function. The initial placement of each quad can be quite far from its optimal position, and we therefore use an exhaustive search routine to reduce the risk of getting stuck in a local minima. Another reason for using this approach is that while modeling, it's important that the procedure is unobtrusive and doesn't slow down or hamper the workflow. It is therefore preferable if this routine have predictable time characteristics. At any time during modeling, the user can choose to activate a global optimization routine. This routine applies to all quads, or a selected subset of quads, and tries to align to the photographs according to the given score function. This comes down to minimizing the energy function with respect to vertex positions, which, as we saw before, are constrained to lie on the view ray corresponding to the views it was constructed from. We compute the gradients with respect to vertex positions along each ray and solve this energy minimization problem by using a standard gradient descent algorithm. The partial derivatives are computed using finite differences. Both the global optimization and the exhaustive search are implemented on the GPU using CUDA for performance. For the exhaustive search, a list of possible quad configurations are sent to the GPU, where they are evaluated according to the given energy function. For the global optimization, quads corresponding to central differences of the vertex positions are instead evaluated for computation of the gradients. Each kernel processes one quad per thread. As long as the number of quads processed are sufficiently high, the GPU utilization is also high. I will now show some results of models that have been reconstructed using our prototype application. First, I have an example of a piece of cloth reconstructed with our method. We can see that we have a nice topology in the leftmost picture. And if we compare a textured version, the middle image, with a reference photo, we can see that we have a high likeness to the original. Note that the photo on the right has not been used while reconstructing the object, but is just used here as a reference. I will now show some results with regards to the topology of the reconstructed mesh. We have compared our interactive method with an open source photogrammetry pipeline called Meshroom. From left to right, we show our reconstruction at 3 levels of subdivision. The leftmost image corresponds to the coarse mesh that the user has to model manually, while the other 2 are largely the output of further subdivision and optimization. We can see that we achieve a favorable topology throughout the subdivisions, and important lines and seams are preserved. The topology of the model created using photogrammetry is shown to the right. As we can see, this model is highly tessellated, and we have to zoom in to actually be able to see the individual triangles. I will now continue with examples of reconstruction quality. Our example is in the middle, and we once again compare to the output from Meshroom. The leftmost image is the raw output from photogrammetry. The rightmost image is a resampled version of the same. In this example, we can see that the automatic algorithm fails to capture much of the detail. It also has problems following the silhouette of the object correctly. In this example, we can see that the automatic algorithm have problems with the crease in the cloth, which is very noisy. In the resampled version, we can see that details are lost. We can also note that it's hard for the automatic algorithm to separate the table from the cloth in this example. Here we can see an example where the automatic reconstruction fails. In the green area on top of the plastic toy, there is not enough texture for the reconstruction to work properly. Our method can handle this, however. This works because the user can construct large quads to cover the whole flat green area. These quads are anchored by the textured regions on their edges. When these large quads are subdivided, our smoothness constraints keeps noise from being introduced. Finally, here we see a short animation of a comparison between our method and Meshoom. Again, our method is less noisy and manages to cleanly separate foreground from background. Our application is just a simple prototype, which is meant to illustrate the main idea of using a multiview stereo algorithm in combination with quad modeling. However, it is far from being ready to be used in production. An interesting follow-up idea would therefore be to implement the same functionality as described in the paper, but in a professional modeling program such as Blender or Maya. To conclude this paper, we present a user-guided system that can be a compelling alternative to automatic 3D reconstruction, followed by a post-processing pass. Thank you.
Hi, I'm Tomer Weiss from the New Jersey Institute of Technology, and today I'm going to present our paper titled Fast and Scalable Position-Based Layout Synthesis, which was published at the IEEE Transactions on Visualization and Computer Graphics. I will start our presentation by clarifying what layouts are we talking about today. To be specific, we're talking about furniture layouts. A quick online search shows examples of what we mean by furniture layouts. Such layouts are the result of arranging furniture in a space. Creating such furniture layouts is a difficult task and is related to artistic content creation, similar to an artist creating their clay work of art or a wooden model of a building. In virtual 3D land, typically artists and other content creators are tasked with creating a layout for a virtual space, a task which is mostly manual. Here's an example of what such layout creation task entails. Notice that the typical workflow involves domain knowledge of a 3D modeling tool and is quite involved. Layouts have been the topic of increasing interest in recent years. Researchers have proposed multiple methods for the synthesis of layouts, their style, light conditions, and also their arrangement for marketing shots. In layout synthesis research, recent work is data-driven and utilizes deep learning. Other prominent work views layout synthesis through the lens of a probabilistic mathematical optimization problem. Data-driven approaches have become increasingly popular in recent years. While such approaches are effective in synthesizing layouts that match existing scenes, they cannot synthesize new scene types. For example, if we do not have a kitchen in our dataset, such methods cannot synthesize a new kitchen. Furthermore, scene datasets have become difficult to obtain. Most similar to our work is the work of Yu et al., which views layouts as a mathematical optimization problem, where the layout energy should be minimized to increase the quality of a layout. Our approach to layout synthesis assumes the user has selected several furniture pieces and is trying to automatically design a space with such objects. Our work is focused on the machinery to achieve such results with limited user input. Let us zoom for a moment to analyze how layouts are structured. A chair should be positioned close to the desk. A plant is placed close to a wall. Obviously, furniture should not occupy the same physical space. And placed furniture should also observe certain aesthetic constraints. Here, the seating is facing the television and is placed symmetrically. The common feature of all such constraints is they can be defined by geometrical equations. Hence, the question is how to design a procedure that will satisfy such constraints and is fast. Our contribution lies in the novel machinery for interactive layout synthesis, which is fast even for large-scale layouts, resulting in virtual layouts in seconds. The machinery we use for such end is physics-inspired. In recent years, position-based dynamics, also known as PBD, has become increasingly popular for the simulation of deformable bodies and has attracted many users, especially in industrial visual effects and game engine software. PBD's strength lies in its ease of control and interactive results even for tens of thousands of particles. PBD was originally used to simulate deformable elastic objects. Objects are defined by particles, and the constraints between such particles define how an object will move. We will now overview a constraint example. Here are two particles in positions P1 and P2 that are constrained to be separated by a distance d. During each simulation time step, we want to maintain this distance between them. PBD models this as a distance constraint. The distance between P1 and P2 should be equal to d. The constraint equation C is equal to 0 when it is satisfied. Alternatively, we might want particles 1 and 2 to be no closer than a minimal distance d from each other. To that end, we can replace the equality with an inequality. Now let us assume that during the simulation, particle 1 and particle 2 move away from each other. We now need to fix this somehow by finding a positional correction delta P1 and delta P2 to satisfy our distance constraint. PDT restricts the positional correction to be in the direction of the gradient of the constraint. A scalar, which is a Lagrange multiplier, determines the magnitude of the positional correction. We restrict the correction to be in the direction of the gradient. PDT linearizes one constraint at a time and projects it into the constraint manifold. We plug delta x back in the first equation to get the last equation. In our method, we abstract the distance relationship between furniture pieces with PDT distance constraint. Please read our paper for more constraint examples. Now I'm going to review several results of our method. Here is a stage scene that is computationally intractable to synthesize with previous work, but is feasible with our method. The stage scene includes several constraints. Distance constraints disallow chairs from occupying the path illustrated in yellow. Chairs are said to be in a certain distance from the center of the stage. Constraints enforce that no chairs occupy the same space. Such group of constraints allow us to synthesize this scene. However, note that the chairs might not be placed in an organized fashion as we would expect in a theater. To that end, we modify the constraints for this synthesis experiment. Here we restricted chairs to lie at specific tiers. Tiers are defined to maintain a pairwise distance from other tiers. Also, within a tier, chairs maintain pairwise distance constraints. We also added pathways to allow passage to chairs. Please see our paper for more details. We shall now compare a method to related previous work. Previous work employed a statistical optimization approach based on Monte Carlo Markov chain. Such methods are purely stochastic and optimize a layout by sampling from different layout configurations, a process that is slow and inefficient compared to our method. And here's another comparison, showing a living room synthesis. Notice that previous work fails to accommodate constraints, since their optimization machinery does not easily incorporate local knowledge. Rather, it is driven by the global energy of the layout. The red circle illustrates the point of failure, where we have an overlap between several furniture pieces. And here is a zoomed-in view. To conclude, we can synthesize a wide variety of layouts, from the layout of a small desk to a large theater. One application of our system is in supporting interior design. For example, other than synthesizing furniture arrangements for virtual worlds, we can also synthesize furniture arrangements into 2D images. For more details about this work, please refer to our CVPR 2017 Vision Meets Cognition workshop paper. Our method has several limitations. A user has to pre-select appropriate furniture pieces for our synthesis and then encode the layout constraints. While encoding constraints is straightforward, it is not immediate for a novice user. Furthermore, such process has to be repeated for each target synthesis. In the future, we plan to address such user challenges by adding a user interface that allows to easily encode constraints. We also plan to explore how to automatically learn layout synthesis blueprints from data or with minimal user guidance. To conclude, we presented an interactive layout synthesis method which is inspired by position-based dynamics. Similar to how PDT adjusts a deformable model to fit elasticity constraints, our method adjusts a layout to fit aesthetic and interior design constraints. Finally, our method is the first to demonstrate computational interactivity for large-scale layouts. Thank you for listening.
Hi, I'm Chris.
Hi, I'm Xiaowei.
We present our paper, Progressive Regularization of Satellite-Based 3D Buildings for Interactive Rendering. Our work is enabled by two observations. First, buildings and other man-made structures often have regular properties, such as parallel walls, fixed degree angles, symmetry, and alignment. The second observation is that, while satellite imagery can be used for large-scale reconstructions, the results typically suffer from occlusions, shadows, noise, and incomplete coverage. In spite of these challenges, our method automatically creates lightweight procedural buildings from satellite-based point clouds. Our approach consists of two stages. First, building point clouds are used to create a tree of layers and a set of line segments for each layer. In the second stage, we pursue a set of regularity constraints inspired by our first observation, producing a watertight and crisp procedural building model. From observation 1, we define an extensible set of architectural priors consisting of symmetry, in which parts of a building are reflected across a discovered axis, parallelism, where multiple walls appear at the same angle, predetermined corners, where walls meet at a set of standard angles such as 90 degrees, 135 degrees, etc., and alignment, where nearby walls on the same or different levels are aligned with each other. To enforce these architectural priors, we take a set of procedural parameters Pi that define a building with such properties. Then B of Pi is a generator function that produces a building model. We want to maximize a hypothetical function A that takes maximal value when B of Pi equals the ground truth. Since we don't actually have the ground truth, we instead maximize this expression as a proxy, where R quantifies the regularization with respect to the architectural priors, and S measures the similarity to the input point cloud, with alpha as a balancing parameter. Intuitively, by balancing regularity and similarity, we arrive at an optimal combination with regards to the unknown ground truth. The regularization is calibrated using a small set of buildings with known ground truth. This is done by finding the parameters that minimize the difference between our balanced objective and the ground truth evaluation. These parameters can then be used at runtime to produce crisp procedural models despite the noisy and incomplete satellite image inputs.
Now, let's move on to describe the first phase, layering and polyline creation. To perform the layering, we first place all points into a grid with voxel size equal to satellite image pixel size of 0.3 meter. Then we use a relative layering threshold to determine the boundaries between layers using the intersection of union of adjacent horizontal voxel slices. We choose a single representative voxel slice for each layer based on closest similarity to all other slices within the same layer. Here is another example. As you can see, our layering scheme produces a tree of layers as opposed to a linear array of layers, because a building might have non-adjacent segments of the same height. Next, for each layer, we use a ransack-based method to determine light segments with a sufficient number of points. To form the closed polyline, our method uses several heuristics. Almost collinear and close-by light segments are replaced with a best-fitted single light segment. And if they are not close enough, start and points are connected as illustrated in the example figure. For segments that are almost coincident, light segment start and points are snapped together. If they are far away, start and points are connected as shown in the example figure. More examples are shown here. Let's move on to the second phase, regularization. In this phase, we iteratively alter regularization parameters so as to reduce the difference between the values produced by the similarity and regularization matrix until producing an output of desired detail or crispness. The similarity metric computes the intersection of union between the current polyline and the original polyline of a layer. The regularization metric makes use of several sub-metrics explained in the following slides. The goal of the corner matrix is to find an optimal polygon where the corners close to 45, 90, or 135 degrees are forced to those special angles by maximizing an optimization function. The function is an accumulation of all corner scores, and a corner score is defined to be proportional to the angular difference between the desired angle and the actual angle. As shown in these examples, after regularization, the corners, both inter or intra, satisfy the spatial angles 45, 90, or 135 degrees. The goal of the wall matrix is to find an optimal polygon where two segments close to be parallel are forced to be parallel by maximizing an optimization function. The function is defined in a similar way. As you can tell in those examples, after regularization, the wall, both inter or intra, are parallel. The goal of the symmetry matrix is first to find the most possible symmetry line L by maximizing the intersection of union of input polygon and the symmetric polygon based on L. If the intersection of union is bigger than a threshold value, we first consider the input polygon is symmetric, and we are trying to alter the polygon points to make it symmetric. Here are two examples for your illustration. We show more building examples where you could find the difference before applying regularization metrics and after applying specific metric terms.
Here we show some results from our paper. In the top table, we show the average number of vertices, edges, and faces of our procedural buildings. And in the bottom table, we show geometric accuracy in terms of 2D and 3D correctness and completeness. Despite the low poly count, our results achieve high accuracy scores. We visually compare our approach to a similar set of prior methods, including Poisson surface reconstruction, 2.5D dual contouring, QSlim, and polyfit. Our method is the only one that maintains the expected geometric and architectural properties. We also visually compare to a similar work done by Leota et al. On the left, also using satellite-based point clouds. While the regions shown are different, the quality of our building models are noticeably cleaner and crisper. Here are some example building close-ups comparing the input point cloud, geometry, projective texture mapping, and aerial photographs. And here we show our building models placed in Google Earth, using synthesized facades from our recently published work in ECCV. We have presented a method to automatically reconstruct crisp and compact procedural buildings from satellite-based point clouds, suitable for interactive rendering and projective texture mapping. Our pipeline determines a tree of layers and a set of architecturally inspired regularization metrics to produce a building model. Our approach does have some limitations. We are not able to automatically calculate global parameters. Particularly non-regular buildings are challenging. We only support flat roof structures, and we only assume 2.5D buildings. These are avenues of future work. Thank you for listening to our talk. For more details, we refer you to our paper.
All right, welcome back to the Q&A session for session 3 of I3D. We have our speaker that should be on video right now. Just reminding you, it's Aoba Jin, Zverker, Thomas Weiss, and we have Xiaowei Zhang and Chris May on video. We have questions actually on the Discord channel. So if you guys have more questions, please post them there as well as on the YouTube live feed, and we'll be picking them up. So we have about 30 minutes to answer questions. So let's start from Aobo's paper and contribution. So the first question is from Johannes Rajala. And the question is, how far do you think we are still off from being able to sketch a car and have a reasonable model? And specifically, he's asking about slide 5 in your talk. Go ahead, Aobo. Unmute yourself.
Okay. In my opinion, to model a car is really complicated from a sketch. So in this slide, only a shell can be modeled with simple 3D sketch lines. But there's a lot of details, such as the wheel and some more little details is easier to draw but hard to model. So I think there's a long way to go to model a reasonable car.
All right. A second question is from Thomas Weiss. And the first question, actually, there's a number of them. The first one of them is, can you please give it more, a bit of details about the implementation? In particular, what sketching interface do you use? And are the results interactive, and whether the code will be available online for this?
Actually, I didn't implement the interface, but the pipeline is easy to use. I only use the application to paint the sketch and generate a 2D image, and then I feed the 2D image to the model to generate the desired model. So that's it. And maybe I will try to do a interface later and share the code. Yeah.
Cool. The next question is from Mateos on Discord, and he's asking about your choices of network architecture. So how did you design your neural net for the task at hand?
That's a good question. Actually, we want to combine the 2D and 3D together in an embedding space. So this so there's only architecture we can use is autoencoder to encode the 2D and 3D features to embedded space, and we can decode them to use the reconstruction loss. So so for 2D, I choose VAE since VAE is more concerned than traditional AE autoencoder. And for 3D, so we just project the features onto the builded latent space, latent 2D space. So we just use autoencoder.
Cool. And I will ask a question myself, if you don't mind. And my question will be, so right now in your interface, you essentially create a prescribed viewpoint interface, right? Where the object is always seen from the 3 canonical axes. And do you have an idea of how this could be extended to have viewpoints from non-constrained directions?
I think that's the same. I use 3 since I think 3 can be provide enough information to model the man-made object or the simple object. But if we provide more details, more views to the model, we can also find the representation feature on the embedded space, and we can just use a decoder to generate the model we desired.
All right. Let me maybe swap to the second presentation, and then we can come back to you, Abo, for more question. You can leave the video on, by the way, just the microphone needs to be muted. So the next question is for Sverker from Johannes Rajala. This says, interesting idea. The first question is, are you actually planning to create an application that integrates into commercial tool for your paper?
Well, as I mentioned in the talk, it's something we have thought about. We haven't done it yet, but if we get the time, it's something that we would like to pursue. But maybe we could do it as we're thinking we could maybe do it as a master's thesis or something like that. But we'll see.
And the second question that Johannes said was, did you try the method with natural environments such as tree, foliage, basically unstructured input?
We haven't tried it specifically for any like trees and foliage and stuff, but I don't see any reasons why it wouldn't work. It basically has the same limitations as any other method that uses multiview stereo or stereo reconstruction.
And connected to this question, I guess he's asking, do you think there are some types of objects that are too difficult for the user guided method where you will have to be more automatic, essentially?
Well, if you care about topology, which is one of the main points here, then, I mean, if you have a very complicated object, then obviously it's going to take time to model that. But if you use photogrammetry and need to retopologize a complicated object, that's also going to take basically an equal amount of time. So, yeah. Okay.
There is another question from Mateos on the Discord channel, and he's asking Sverker, how much time does the manual process in your method take compared to a classical retopology process made by an artist?
Yeah, so I mean, I don't have any hard figures here, but I would say that the process is fairly similar. And once again, here our main point is that it's sort of better to put the effort while you're reconstructing than doing it afterwards. I mean, for example, if you have an error from the photogrammetry or an automatic method, then you just have to sort of manually guess what the best what the geometry should look like. But in our case, you can probably work around it in some way instead.
Sounds good. All right, so let's move on to the next paper, which was 1, 2, 3, fast and scalable position layout synthesis from presented by Tomer Weiss. I don't think I see a question on the Discord channel yet. Please do post it. So I'll go ahead and ask. I'll ask my question. So you're using a PDT constraint solver, right? Which is designed for physics. And my question is, the physics part, was it really bringing to the mix? Is it because when you create a layout, interpenetration of objects is such an essential constraint to be respected, and so essential that that's the main reason for which the physics engine need to kick in, because you could use any constraint solver from.
Yeah. So that's a good question. So we tried different constraint solvers, including very simple and very advanced ones, and we saw that they usually are not flexible enough to create a layout from different starting kind of random locations of furniture. So that's where like that PBD engine comes into play. We saw that experimentally it was really working most of the time. So that's why we used that.
Understand. Interesting that
yeah,
there was nothing on the market for a more like general constraint satisfaction problem. The second question, I think I'm going to go ahead again and ask it myself because I don't see anything on the Discord. But yeah, you're posing a user-guided under constrained optimization problem, right? So in theory, there is an outspace of solutions to what you're doing. And I guess one of the neat way in which you're using physics is that physics gives you conditioning to the problem, because the temporal aspects essentially narrows down your solution, correlating it with the initialization. And my question is, have you tried to quantify how much null space is left after a set of constraints is specified?
What do you mean by null space?
Well, the null space is how big your variety of scenes that you can generate, right? And if you are too constrained in your constraint, you're going to get one solution or potentially no solution at all, right?
So that's a great question, and that's very hard to quantify. So what we saw is different initializations can give you different solutions. And even though some solutions might not satisfy all the constraints, people usually sometimes like them. So that kind of leads to the bigger question is like, maybe such constraints are not really capturing what people want in a layout. So that kind of gives us kind of more research directions, and maybe it's better to, first of all, kind of limit what people want by kind of minimizing the search space. Like, you know, I want a bedroom, and then, okay, how many people will be in the bedroom? And then by that, you can maybe use that to kind of narrow down the scope of the problem. Because the problem that this engine is solving is pretty big. If you think about it, it's taking like noise, random noise, and transforming it to something that kind of makes sense for people, for us to use. But that's kind of a very hard problem. So it makes more sense to constrain the problem like even before that engine comes into play.
All right, let's go to the fourth paper and then cycle back again. So the fourth paper was presented by Xiaowei and Chris. So please unmute yourself. And we have a question from the Discord channel, and it's from Johannes Rayala. And the question is about limitations. What do you think will be needed to be able to produce buildings like these? And has the skyline of Shanghai as an image posted on Discord. You can replace it for New York if that's more familiar for you. But
yes, so I think our paper is a very good fit for this Shanghai skyline, because we are focusing on the whole region to generate nice buildings. But however, as we mentioned in the limitation, for buildings with like not flat roofs, we cannot generate the non-flat roof. That's the only limitation I can think of. Chris, do you have anything to add?
I would say, I think maybe some of these buildings are a bit curvier than buildings in other regions. So we might have to calibrate to the specific region of those buildings. The different parameters for the regularization make a big difference depending on the buildings in the region. So might be another issue.
And I guess I will ask a second question myself. So well, these days I'm a machine learning person. So the natural question to me becomes, have you thought about converting this pipeline that uses more like traditional methods in 3D geometry and vision to a more end-to-end solution? And where do you think the interesting problems in that are?
So, I mean, there are like a lot of like deep learning based approaches working on 3D geometry reconstruction. However, for still light, we didn't find any like prior work working on using deep learning. So that's why we start with the more traditional way to do this.
Do you see any challenge in being able to use these methods? Is there any part of your pipeline that you think that was maybe more painful to construct by hand, and where data would have helped you in designing a more effective and performant solution?
I think the most important part and the most challenging part is how to tune the parameters for the whole region such that it can work perfectly on the whole region, not individual buildings. Yeah, that's the most challenging part.
All right. Okay, so we have still 10 minutes. So I'm going to cycle back to the questions that were not answered. I'm going to restart from Aobo. We had part two, sorry, of the question from Tomer Weiss from earlier. Did you consider using handcrafted rules to refine the volumetric results of the sketches? For example, the output might appear a bit fuzzy. Perhaps within each class of shapes, there is some common sense of topology that you can use to make your retrieved output look more elegant.
Yes, actually, for the handcraft rules, I think the autoencoder thing learned the rules from image and can generate the desired 3D model. So I didn't consider add more handcraft rules to the network. I just want the network to learn these rules. And yes, maybe for if we have a large 3D data set, and we can use the generated model to retrieve more detailed 3D models to make the result much more better.
Mm-hmm. And the next question, let me see. I think I'll ask one from my pool for Sverker. So for the next paper, so user-guided 3D reconstruction using multiview stereo. So Sverker, do you think, so looking at your interface, which by the way looks awesome, because I spent a lot of time in the past trying to do this when I was starting to play around with Blender, and it was really painful. Yeah. But the question looking at your interface would be, would it be possible to reduce the topological modeling aspect of it, in the sense that, when you look at an image, a human can tell, okay, I want to put a quad in this region. So could you provide something that does some form of autocomplete proposal where, in a large variety of cases, like think of it like Gmail autocomplete, right? Like it produces the next sentence. And in your case, it could produce the next topological event to augment your scene. And how would you design that?
Yeah, right. We thought a lot about this as well. Sort of how can you simplify this first step of doing the sort of coarse construction for the lowest level, which you have to do manually. And I mean, there are also a lot of tools in existing modeling programs such as Blender and so on that helps with stuff like this. So I mean, there's a lot of stuff you can do to expand this, I think, and you can also, I think, fairly easy sort of auto-generate guesses for where the next topology should be using the existing sort of multi-view pipeline that you have. Since you have that whole machinery, you can just add a quad somewhere, and you can try to align with edges, for example, and stuff like that. So you can have some kind of simple template thing as well that you can sort of start with. That's bigger than just one quad, and then sort of auto align it to the images.
And the next question that I have for you is required as a precondition. Are you familiar with like neural rendering, neural radiance field kind of works? Is like they've been
yeah, a little bit
become quite popular recently. So
yeah, sure.
So basically, photogrammetry is from a neural rendering perspective is moving a little bit more toward these neural models. And I'm wondering, is like, do you think a method like yours for topologizing a surface could also be extended to leverage these systems that take a sparse set of images and now generate free viewpoint information, right? And how do you think the two could be? And I know this is an open question, but how do you think the two ecosystems could live with each other?
Yeah, that's a very challenging question, because I think the issue that we try to address here is this sort of, how do you get a model that has a nice topology which you can actually use as an asset for something? And that question is not really answered by the neural methods either. I mean, they can produce very nice viewpoint renderings and stuff like that, but they don't really help you with the sort of getting a nice reconstructed object that you can actually just put in somewhere. So I guess the question, the really hard question is sort of where, how do you use those nice new viewpoints and so on to actually create an object that has these desired properties of a nice topology, for example? And at least I don't know exactly what that would look like, or how you would sort of pipe that in, sort of the newer stuff, and connect that with the geometry and the topology in the model in a way that sort of makes sense. Yeah.
Cool. So the next question, maybe let me jump to the Discord channel because I see that there is a new question being asked there. So Tomer Weiss asked a question for Xiaowei. So if you can unmute yourself. What do you mean by whole region? And also regarding the current machine learning approaches, is there any synthetic data set for your domain?
Okay, so whole region means when we tune the parameters, regularization parameters, we are focused on the whole region, meaning the whole city, not the specific building. So for the whole city, we have one set of regularization parameters. We want to make all buildings look nice. That's the whole region mean. And for synthetic data set, maybe for like simpler 3D objects, there are some published data sets, but for like man-made buildings, those complicated things, I'm not sure there are. And,
right.
and also we are satellite based, so I'm not sure yeah.
And next question is for Aobo from the first of the talk, and it's a question from me. So what you're doing in your model is essentially that you're using some form of data set essentially to constrain the global geometry of the objects that you're seeing, right? But when you're an artist, what is really important is localized control, right? So you want to modify a small portion of the geometry to obey some rules, some high-level design guidelines that you have. So my question is, could your method be modified to perform localized editings rather than using global context for the geometry? And remember to unmute yourself. Yes, thank you.
The model have some ability to make the artist to model the exist 3D model. So given a 3D model, and you can sketch some part and generate a new model, but the ability is limited. So if you change a lot, the result will not very good.
All right. I think in this case, we exhausted all questions. So I would like the audience to do a virtual round of applause on YouTube, and we'll see you in the next session. Thank you, everybody.
Hello, everyone. This is the fourth session of the I3D symposium. In this session, we're gonna present two exciting papers. In this session, we care or focus most on the human side of the interactive technologies for perception and performance. So the first paper we're gonna present is the effect of lighting, landmarks, and auditory cues on human performance in navigating the virtual world. It's done by Darryl Maples, Duke Goodhill from University of Hartsfield, and Pelham Carter from Birmingham University. Darryl will present this paper. The second one is the role of field dependence, independence construct on flow performance link in virtual reality. It's from Yulong Bian, Chao Zhou, Yeqing Chen, Yan Shuai Zhao, Jian Liu, and Chenglei Yang from Shandong University. Yulong will present this paper for us. So welcome, Darryl, to present the first one. Thanks.
Hi, I'm Dr. Darryl Maples, and this presentation is the effect of lighting, landmarks, and auditory cues on human performance in navigating a virtual maze. We took the approach of studying virtual environments from a video game's perspective, and in the video game, traditionally you will have some way of navigating through your virtual environment, such as a map or compass or similar implementation of an external cue. But many games recently have allowed for the removal of those maps almost in their entirety, and offer instead ways of navigating through virtual worlds based upon architecture and looking at more intrinsic cues such as distal objects or even more local landmarks. We were particularly interested in the way that many games nowadays will incorporate features into their environmental layout that are based on architectural layout and also more subtle elements such as colour variations, such as climbable edges that have a simple colour variation or a shading variation that tells the player that they can climb on that object. And there are many ways in which players are guided throughout game levels nowadays that are of this nature. The ones we were particularly interested in were lighting and audio. Many games nowadays utilize lighting very effectively to guide players through their games, and we wondered just how effective that was and whether there was a low limit to the amount of light that was required to actually pull a player through a particular level. Obviously, there's a tremendous amount of research that underpins what we are looking at in the literature, stemming from Tolman's early work on cognitive maps through Siegel and White's route connectivity and landmark knowledge research. Much of this research hasn't got a particular games-related bent, but it doesn't really relate to the virtual environments. But later research, such as the work by Vincent et al. In 2009, starts to look at how lighting influences the way in which people navigate through virtual worlds. So our hypotheses were that players would react to even subtle variations in lighting and choose their routes based upon whether their path to a set goal was illuminated or not. We also wanted to look at the impact that audio cues would have, and we hypothesized that players would navigate towards audio, and we also figured that it was worth looking at cue conflicts between these two aspects. So would an audio cue that headed you towards one direction and lighting that suggested that you go in a different direction cause conflicts within our players? We also wanted to look at another aspect of this, which is the colour variation within the environment and see whether colour variation could have any impact at all on solve times. So we decided to use mazes. The main reasons that we chose to use mazes in this context is that they are commonly used within cognitive sciences anyway, but they are of course very familiar to people. Everyone has the concept of what a maze actually is, and also simultaneously they allowed us to have visual uniformity without breaking the immersion of our environments. What we decided to go with in the end was a central goal maze. We had run a pilot study where players used the left-hand rule to find the exit to a maze. So we went with a central goal maze, which allowed us to alleviate that problem. You cannot solve a central goal maze by just tracing around the edge. You'll end up back where you started. All our grids were based on a 23 by 23 block structure, and what we had as well were mathematical similarities between each of our layers. So what we have is 3 concentric islands, and we have 14 3-unit dead-end turns in each of our mazes. In total we created 30 mazes, this is demonstrated on the slide. We incorporated each of our 5 lighting variations, so there was a neutral, a red and a lit path variation. We also had a dark path that led to the goal as well, so every part of the environment would be uniformly lit except for that path, and then we had our red and blue variants as well. We had 3 audio variations, one with no audio at all, and then audio at the goal and audio silent at the goal, but as you can see in the image, we had audio cues positioned at the perimeters, so you would be forced to navigate to the perimeter and not to that central goal. Here are some examples of the visuals of what our levels actually looked like. So figure 1 shows with graffiti, figure 2 shows without graffiti in a uniform lit state, figure 3 a red lit state, this was done by a hue shift, and figure 4 the blue state. We had 134 participants, 115 of which were male and 19 female, average ages 17 to 54. The results that we achieved were very interesting. What we found was that yes, lighting does have a major impact, and this was statistically significant, and that didn't come as any surprise. We expected that to be the case. What was interesting was that we also found that the lighting and audio combined didn't lead to the audio itself having a significant impact on top of the already significant lighting impact. So whilst you can see from this graph the audio did have an impact overall, it wasn't deemed to be statistically significant when combined with lighting. However, audio on its own, again as you can see from the graph, was statistically significant. So the reinforcement effect was not as strong as we initially anticipated, but we were pleased to say that the audio component did have a major effect when it came to participants navigating towards specific areas of the mazes. We included graffiti as a landmark type. We didn't find in this instance, using graffiti as our landmark type, that there was any significant effect of graffiti as a landmark, which was quite a surprise, but it was quite subtle. And again, I'll come back to this at the end of the presentation, but it is something we want to address in future work. We also didn't find that the graffiti as a landmark type reinforced the effect of the lighting either. So for neither the audio nor the lighting component, we weren't able to find any significant effect of adding graffiti to the environment as far as solve times were concerned. So our key findings overall were that mazes are solved faster if you demonstrate a subtle amount of lighting variance in that environment, giving the players something to follow. Similarly, mazes were solved faster where there was an audio component located at the goal of the maze that players again could navigate towards, and conversely, where that audio component was positioned at the exterior of the maze, participants solved the mazes actually slower. We weren't able to replicate the effects of a prior study that stated that under certain colour conditions mazes were solved faster. In fact, we saw very little variation between the neutral state and the two colour variations. So our conclusions overall is that lighting in a virtual environment can be a very effective method for guiding players through that environment. It is effective even when it is subtle and it is not presented in a way that makes it clear that that is the cue that is meant to be followed. And we found a similar effect for audio. We didn't specify a particular type of audio for this experiment. In fact, we used quite an off-key piece of audio in general, and we still found that our participants gravitated towards the source of that audio component, whether it was at the goal that they were anticipating or whether that was at the outer extremities of our mazes. Therefore, positioning audio within an environment, if it is not key to navigation, can actually lead to cue conflicts. So, as far as our future work is concerned, we found this entire process very interesting and the results themselves were fascinating. So we are very interested in taking this research further forward, and we intend to analyse what the thresholds for lighting of this type are. One of the things we actually want to do is take this work into a more current and up-to-date video games engine that's got a better lighting solution, and we would really like to take this into VR. Again, that gives us additional control over the actual lighting conditions within our environment. The other thing we would like to do is analyse why we found this problem of landmarks in the form of graffiti not actually being effective. So we would like to study the graffiti component in isolation and then maybe look at introducing props of some kind as a different kind of landmark and see if a neutral landmark based upon an actual prop landmark based upon a piece of graffiti creates any differences in solve times. And then finally, we would like to analyse further the types of audio used. We've already demonstrated very clearly that people will gravitate towards audio, but we want to look at what types of audio will have different impacts on player navigation. Okay, thank you for watching.
Hi, everyone. I am Yu Longbian from Shandong University of China. It is my pleasure to share one of our recent work. The topic of this work is the role of the field dependence-independence construct on the flow performance link in virtual reality. When it comes to user experience in VE, flow experience is a hot point. It represents a highly enjoyable mental state, where the individual is fully immersed and engaged in the process of the activity. It is even known as the optimal experience. One reason is the strong flow performance link. It means achieving flow can contribute to the enhancement of performance. However, the flow performance link in VE is commonly weak, which has been proved in our previous work in 2018. It is a problem can't be neglected in virtual learning and education applications, because if good experience cannot effectively promote performance, blindly pursuing good experience would be less meaningful, or may even be counterproductive. So, how does this problem happen? The weak association model suggests the reason is that the usage of interactive artifacts is disjointed with the primary task. Here, artifacts include various contents. Using artifacts can also produce flow, which might be independent from performing the task. This flow can directly contribute to better experience, but not directly contribute to better task performance, as the hollow arrows show. If the user pay attention on irrelevant artifacts but lose attention from the task, the flow performance link would be weak. Here is a new question. Is there any individual difference in this problem? We believe people are different in the ability of selective attention or handling distraction. A factor worth considering is the field dependence-independence construct. Short as FDI, it is a polar construct describing cognitive style. It affects the ability of goal-oriented behavior, handling distractions and selective attention. Based on this construct, people can be divided into field-independent, short as FI, and field-dependent, short as FD. FI people may behave better than FD people in these aspects, then show stronger flow performance link. The main purpose of this study is to explore the role of FDI construct in flow performance link, and explore potential approaches to strengthen this link. To examine above questions, a VR testing environment needs to be firstly constructed, according to the primary task distractor paradigm proposed in 2019. We developed a VR undersea searching test from the first-person perspective. In the VR test, the player falls into a mysterious sea and becomes a king crab. He needs to search and rescue some creatures. By using HTC Vive, a near-to-real roaming experience is simulated. By simply using a swivel chair, the player can move like a crab. To explore the weak link, the primary task and disjointed features need to be designed. Here, the primary task is to search and rescue 8 marine creatures within 4 minutes. During doing the primary task, various sea creatures are designed as distractors to randomly navigate in the scene, to distract players' attention and interests. Interacting with them is available, but it is irrelevant to the task. Based on this VR system, we conducted 2 empirical studies. Study 1 is to test the difference in distraction and flow performance link between FI and FD individuals. We supposed that when performing the primary task, FI individuals would do better in refusing distractors and show a stronger flow performance link than FD individuals. 15 FI and 15 FD participants participated in this study. They were selected through the Chinese version of the group embedded figures test. Their previous experience of VR was controlled. After practice, all participants experienced the formal VR game for once. Their flow experience, game performance and distraction were measured. Flow experience was measured with flow short scale. Game performance were recorded by the system. Distraction includes distracted interaction and distracted eye movement. Distracted interaction was measured with the interaction times with irrelevant marine creatures during the primary task. Distracted eye movement was tracked with a glass DKII and assessed with the dispersion degree of fixations. To test the hypothesis, we did a series of independent sample t-tests. Results on distracted interaction revealed that the interaction times of FD participants was marginally significant, more than that of FI participants. Those shown in the pictures are 4 examples of distracted interactions. Moreover, the dispersion degree of fixations for FD participants was higher than FI participants. This difference can also be intuitively seen from the heat maps of 2 typical samples, as the videos and pictures shown in the slides. Results on flow and performance showed that there was no significant difference on flow, but the performance of FI participants was better than FD participants. Next, we conducted 2 regression analyses to respectively test the flow performance link for FI and FD participants. Results from FI participants showed that flow marginally predicted the task performance. In comparison, data from FD participants showed that flow didn't significantly predict task performance. These results supported the hypothesis, proving that FI individuals do better in handling the distractors and showed a stronger flow performance link than FD individuals. According to the weak association model, a potential approach to strengthen flow performance link is enhancing the congruency between task and interactive artifacts. Then, study 2 is to test the effect of congruency design on the flow performance link for FD and FI individuals. We suppose that improving the congruency features of BES have positive effects on the flow performance link, especially for FD participants. 28 FI and 28 FD participants participated in this study. Their previous experience of VR was controlled. Different from study 1, this experiment adopts a 2-factorial mixed design. The within-subject factor is VE type. Therefore, we need to prepare 2 versions of BES in this study. Here are the 2 versions of VE. Version 1 is the disjointed VE. It is same as study 1. Version 2 is the congruent VE. Based on version 1, version 2 increases the congruence between distractors and primary task. It provides implicit visual cues to utilize distractors to achieve more task-oriented attention. More specifically, in version 1, after interacting with the marine creatures, they still move randomly. But in version 2, after interacting with the marine creatures, they will move more frequently towards the location near the treasure chests. After practice, all participants experienced the 2 versions in a specific order. Their flow experience, game performance, and distraction were measured. Most of the measures are the same as those in study 1. The only difference is the distracted interaction is removed from the measures, because interactions with distractors creatures in congruent VE are no longer completely irrelevant to the primary task. To test the hypothesis, we did a series of repeated measures ANOVA. Results on dispersion degree revealed neither significant main effect nor interaction effect. But if we look at the descriptive statistics, the dispersion degree of fixations for FD participants is still a little higher. When looking at the results on flow, neither main effect nor interaction effect was significant. When looking at the results on performance, there is a very significant main effect of VE types. Congruent VE led to better performance than disjointed VE. Next, we focused on FD participants and respectively test the flow performance link in the two different VE versions. Results of regression analysis shows the flow performance link in congruent VE is much stronger than disjointed VE. These results support the hypothesis, proving that improving the congruency between task and potential distractors in VE helps strengthen the flow performance link of FD individuals. In summary, in this paper, we clarify the difference between FD and FI people on the flow performance link. FI people do better in refusing the distractors and show stronger flow performance link than FD people. Moreover, we verify an approach for strengthening the flow performance link in VE, which is to enhance the congruency between task and interactive artifacts. More specifically, that is to provide implicit visual cues to utilize distractors to achieve more task-oriented attention. This study still has some limitations. First, the measuring method of eye movement is not ideal enough. Current eye tracking devices cannot match the eye movement fixations with specific objects in VR when drawing heat maps. Therefore, we cannot get what objects they are paying attention to. Second, the system used in this study is a VR game. In fact, to examine the flow performance link in virtual learning and training system will be more meaningful. In future research, we will fix these shortcomings. Thank you for your attention. If you have any question, please feel free to contact me.
Hello, everyone. Welcome back. Now is our Q&A session. So I'll group the questions to the authors and presenters by the paper order. So we're gonna answer the questions for the first one by Daryl Mampos, who present the paper and will answer our questions. Daryl is a senior lecturer and course leader in game design, in video game design. He's interested in analyzing 3D visualization, perception, and navigation. So he has 15 years in game design and higher education experience and 12 years prior experience on creative field. Daryl has been in this field with fully experienced research and development. So for the question to Daryl, let's start with the question from Naty. The first question is, do you think the cues will be more effective in virtual reality? I think comparing to the regular video setting up.
Yeah, I think my gut instinct would be to say yes, probably. I think the issue really for us, if we're going to continue the study in VR, which was our intention, of course, you know, circumstances have changed over the last few months, but our intention is to do this in VR, and it's a matter of judging the lighting so that it is more or less sub-perceptual, so you don't notice it. The intention in the study really is to test lighting at 3 different thresholds and see if you get the same effect when the lighting really is below it's there, but it's below a perceptual threshold.
Thanks for the answering. If there's any follow-up question, feel free to post to the channels. And the second question also from Matt is it possible that multiple resources may produce less or like a lower performance? I think compared with one single dominant audio versus background noise, would standout primary audio still be the major contributor to the effect?
Yeah, I've got to say thank you to Matt, because I think he's just designed an experiment for us. I think it's a great question. I don't know the answer. I want to find out. Yeah, it is entirely possible. I mean, we actually chose quite an aversive sound, something we thought that people wouldn't have any inclination to head towards under normal circumstances, but it was utilized as a navigational cue, and that noise was basically quite spooky in nature. So we are intending to again, once things go back to normal, to do more experiments on different types of audio. I've just taken on a master's by research student to do that work exactly.
Yeah. Thanks for the answering. Studies are really challenging these days, especially with
I know.
users.
We couldn't have planned for this at all. No one knew it was going to happen.
Yeah. So maybe every study has to go virtual. I have a question from myself. A very interesting talk and very creative innovations out there. My question is, so I assume that right now the study is done by like a mouse and keyboard or gamepad type of navigation. So did you test either, for example, with like a real walking from the virtual reality? Would people have like more frequently to rotate their head and things like that? Would that introduce different behaviors compared with?
We are yet to find out. Again, these are questions that we want to analyze. We were meant to be analyzing them right now, but of course things have got in the way. So they're certainly on our radar.
Yeah. I think that could be interesting. The different user behaviors are discovered with different settings.
It's also down to whether users are used to VR. We were fortunate that the people that volunteered for our study were used to playing computer games. They needed at least to understand sort of like keyboard input or keyboard and mouse input to navigate in a video game, and the vast majority of those people that took part did. With VR, that's very different, because there's a smaller subset of people that have got that VR experience.
Yeah. That could be highly diverse among different user backgrounds. Thanks for that. I think a related question is how much that would affect the, for example, simulator sickness. Would that introduce additional fatigue, or I mean, with different settings, for example, the audio, the lighting, does that change or affect the comfort in the experience?
Well, I've played quite a lot of VR games, and video games, as I said in my talk, have utilized these methods to draw players in a very obvious way. But there's a lot of subtle things that are utilized throughout video games that do engage players without them actually realizing that they are being dragged in a particular direction. It's certainly something that we want to study in more depth going forward.
Let's just get to model, I guess.
Yeah.
Thanks for the.
All right, so that's the end of the second day for I3D 2020. We hope you enjoy all the discussions, the keynote, and the technical papers. So as I was saying, today was the second day. Tomorrow we have the third day. Remember that tomorrow we have also the virtual poster session, which we encourage you to join us. It's going to be a virtual experience hosted in Mozilla Hubs. So everybody is welcome on that session. You should click on the link that we provide, and then you should be able to join in a 3D and virtual environment where you can interactively browse the poster session and chat with the others. So I encourage you to join for that very special session that we have tomorrow. And remember that tomorrow we start again at 9 a.m. Pacific time, and we hope to see you all there. See you tomorrow.